looking at problems that started with a log in them. We've also solved exponential equations, but we were always able to get a common base. Sometimes that's not possible though. If I gave you something like 2 to the x equals 9, can you rewrite 9 as a power of 2? No. So we still have to be able to solve these types, and that's what we're going to start doing in this section. To do that, we have really two properties that we're using. Today we're focusing on this first box. So we're going to start out with exponential equations. If two things are equal, then it's true that the log of each thing is equal. So essentially this is telling us we can add a log to each side of an equation, and it's still true. So we use this in situations where we can't get a common base. So for instance, our first problem, 8 to the x power equals 21. Okay, obviously common base is the easiest option. I could rewrite 8 as 2 to a power, but can you write 21 as 2 to a power? No. So what we do instead is that property of logs, which says we can add a log to each side of the equation. Now technically you could add a log of whatever base you wanted. If I don't write a base, what base am I assuming? 10. We like to either do log base 10 or a natural log because those are the two buttons we have on our calculator. So we're always going to stick with one of those. Now, initially this may not look better, but think about properties of logs. If you have an exponent, what can you do with that exponent? Move it to the front. So this is x times the log of 8 equals the log of 21. So then how would you get x by itself? So x is log of 21 divided by the log of 8. All right, we could give our answers different ways. Your assignment today is going to be Math Excel. If it says give the exact value, that's this. But I might also ask for a decimal approximation, in which case we plug it in our calculator. I want everybody to plug this in. When you put it in your calculator, when you push log, it opens a parenthesis, so you do have to make sure you close that. Standard answer, we typically go 3 to 4 decimal places. I think all the homework tonight asks for 3 places when you approximate. So we get 1.464. Is that what you guys got? Let's check that. If you type in 8 to the 1.464 power, what do you get? All right, why did it not work out exactly to be 21? Because we rounded with 3 decimals, right? So the more decimal places we kept, the closer it'd be to 21. Or if we actually typed in log 21 over log 8, it would work out perfectly. All right, let's look at the second one. So 3 to the 2x equals 1.4. So we check, can we get a common base? No. So instead, what do we do? It's an equation, so whatever you do to one side, you do to the other. All right, the reason this is helpful is because properties of logs. What would we do now? That's when it comes down. All right, x is being multiplied with the 2 and the log 3. So to get it by itself, we divide both of those. So we have log 1.4 divided by 2 log 3. This is my exact answer. If I ask for a decimal approximation, on the calculators, parentheses can sometimes be a problem. So here is my suggestion. If you are using this calculator, then I want you to push the N over D button so you can actually view it as a fraction. If you are using the graphing calculators, I want you to hit alpha, the green button, and then y equals, enter. And so then you should be able to view it as a fraction. If you do not have a calculator, pick one up right now. Because all day we're going to have to plug things in. So make sure you're viewing it as a fraction, then you don't have to worry about parentheses issues. So on the graphing calculator, that's alpha, y equals, enter. So the green button. All right, so we're going to type this in. Log 1.4, close our parenthesis. And on the denominator 2, log 3, close our parenthesis. So my decimal approximation is 0.153. If you plug that in, it's equal to 1.39958, so very close to 1.4. It would be more accurate if we kept more decimal places. Did anyone have trouble plugging that in and you need to look at your calculator? Let's try it. All right, before we add our logs, we aren't trying to make the problem harder than it needs to be, right? If I added a log right now, I would have the log of things being multiplied together, and I'd have to start splitting things up, and I end up with multiple logs, and we don't really want that. So, I tried to kind of break down strategies on these notes for you. You always want to isolate the exponential. Get the exponential by itself before you add a log. What could I do with these? If things are multiplied and have the same base, you add the exponent. So that's e to the 4x plus 1. So now we add a log to each side. Now you can do regular log base 10, but if we have e, what log might be nice? Natural log. If you did the other one, you're going to get the same answer. But here's why this is nice. We know the exponent comes down. Natural log of e means log base e of e. What is log base e of e? It's saying e to what power equals e? 1. Anytime you have a natural log of an e, that just drops. So it just gives us an easier answer to look at. Okay, again, if you had the other log, you would just have to divide it over, so you'll get to the same point. So now to get x by itself, what am I going to do? It doesn't go into my log. It's just on the end. So it's like you're doing the natural log of 4 and then subtracting 1 from the end. And then we divide by 4. So this is our exact answer. The decimal approximation, again, very helpful to view things as a fraction. So alpha y equals. And what do you get? Yeah, that would round up to 0.0966 or 0.097 if you did 3 decimal places. So the only time I usually use a natural log is when I have e's in my problem. But you can technically use it whenever because we have that button on our calculator. All right, let's look at this one. Our strategy. We have to isolate the exponential. So we're trying to get the exponent piece by itself. What would you do? what would you do about this 3? Divide it. I just want, the e is the only thing with the exponent, so I need it by itself. So then we add our log to each side. Because I have e, I'm going to choose natural log. What happens when you have a natural log of an e? That cancels, so you could just say 5x equals natural log of 7/3. And divide by 5. So natural log of 7/3 divided by 5. That's our exact answer. Decimal approximation. And you can always check those approximations by plugging them back in. Can you multiply the 5 and the 3 to the x? No. Order of operations says you have to do exponents before you multiply. Also, it's not helpful for me to add a log here. If I did, I can't bring my x down, can I? Because the whole thing isn't to the x power. So that's why the first step is always isolate the thing with the exponent. Okay, so it's 3 to the x power, so I have to get that by itself. What do we do with the 5? You can leave it as 6/5, you can write it as 1.2, that part doesn't matter. Now what? Yep, does it matter which one? No, there's no obvious easier one here. The only time one is easier than the other is when we have e's, we pick natural log. Okay, then the x comes down by the properties of logs. So we have x log 3 equals the log of 6/5. So to get x by itself, we divide. Get 0.1659, so that would be 0.166. Are we understanding these? You guys walk me through the next one. Good. The 2 is being raised to a power, so I have to get that 2 by itself. Add my 5, divide by 4. I can't get a common base. 20 is not 2 to some power, so then what? We add it to both sides. Exponent comes down. Be careful. That x plus 3, that whole thing is coming down. So that whole thing is multiplied with log 2. So then what would we need to do?
Divide the log 2.
And then final step to get x by itself. It can't change my log, so it's just log 20 divided by log 2 with a minus 3 on the end. That's the exact answer. All right, get your decimal approximation. what does that turn out to be?
1.322.
And if you plug 1.322 into the original, you get like 75.0037, so very close to 75. So we can always check them. All right. I want to do 2 more. How is this one different? Both sides have an exponent. All right, can I get a common base between 5 and 8? No. Since both of them have an exponent, I can't really isolate both of them at once, right? So what do you think we do first? Yeah, we're going to ultimately get the x's on one side, but if you want to go ahead and add the logs first, if that's a little bit easier, we can start there. So exponent comes down. And this one, what should I put around that x plus 1 when I bring it down? I have x on both sides, so it's not as simple as just dividing by log 5 or log 8 here. I have to ultimately get all these x's on one side. What should I do with this log 8 then? We have to distribute it. Now, the x gets multiplied with it. It doesn't change the argument, it goes in front. So we have 2x log 5 equals x log 8 plus 1 times log 8 is just log 8. Trying to get the x's on the same side, so now what should we do? So if I want them on the same side, I'm going to subtract this one over. Now, unfortunately, they aren't like terms because one is log 5 and one is log 8. So I can't actually combine them. I just put them on the same side. So we added our log, brought down all of our exponents, multiplied it out, put the x's on the same side. Have I lost anybody? Okay. Both of these have an x, but I can't add them together. So what else can I do with my x? Wait, let's take it out so we can divide. Okay, we said both things we needed. So if I take out an x, that leaves me with 2 log 5 minus log 8 equal to our log 8. So then to get x by itself, we just divide that whole thing. So I have log 8 divided by 2 log 5 minus log 8. So x's on both sides made it significantly longer. Let's go ahead and plug that in. Make sure after every argument you close your parentheses. So log 8, close your parentheses. 2 log 5, close the parentheses. Minus log 8, close the parentheses. This is the exact answer. What is our decimal approximation?
1.825.
And we can easily check it if we plug that back into the original. If I do 5 to the 2 times 1.825, that gives me 355.828. If I put it in the other, I get 355.819. So we can see they're very close, so you can check them that way. Why don't you guys try this next one? See how far you can get here. It's very similar to the one we just got done doing. log. Exponents come down. Everybody did a good job. You distribute your log. It doesn't change the argument. That 3 can't change. Anything you multiply it with just goes in front. Okay, so I need to get my x's on the same side. Doesn't really matter which side, they just have to be together. So I'm going to add over my 2x log 3. Now both of these terms have an x in it, so what should we do? So really the only, a couple of small things, but I did see some people had a minus here, so make sure your signs are correct. Then to get x by itself, you divide by everything it's being multiplied with. So we should get log 3 over log 4 plus 2 log 3. If I plug that in to get a decimal approximation, I get 0.307. All right, how are we feeling with these problems? Good? Okay, I want to stop here for today. So there is a Math Excel assignment open for just this type of problem, so it's due tomorrow, and you have time to work right.